Alright, so this video is going to try to help you focus down the proportionality if you have a rough idea of what the graph looks like and if you're still not entirely sure about what it would look like. So a couple of the graphs are super easy to read. If you plot voltage versus radius and you get a completely horizontal line, that would mean that there's no effect. So if you measured 10 different distances and the voltage didn't change, that would mean that the radius has no effect on the voltage. So in your equation for voltage, you could have all sorts of things over here. K, Q, gravity. We don't know what those other things are, but we know for darn sure that radius is not on the other side of the equation, because if it did, then modifying the radius would in turn modify the voltage. That's the basis of all of this. We're building equations. So we know that voltage is not related to radius, or is not proportional in any way, shape, or form if this is the graph you get. If, when you plot voltage versus radius, and you get a perfectly straight line of slope m, then we know that voltage is going to have to be equal to some slope times the radius, right? Y equals mx, where x-axis is radius, y-axis is voltage. And this would determine our equation. In fact, you could even find the slope by doing rise over run, y over x. Voltage over radius would be equal to the slope, and you could figure out, hey, wait a minute, voltage equals, let's say you find the slope to be equal to 3, voltage would be equal to 3 times the radius. So that's why we're looking at these graphs so much. That's why we care about them so much. So similarly, if you plotted anything else instead, if you plotted voltage versus radius squared, and you got a perfectly straight line of slope m, maybe it's equal to 2, who cares? You would have to find rise over run to figure out what that slope is. Then we would know that, again, y equals mx plus b, where y is voltage, slope would be equal to 2, and x is r squared. And there is no y-intercept on this graph because we go through the origin. So your equation would be voltage equals 2r squared. And that 2 might be other variables divided by each other. We're not going to get into that for now, because all we really care about right now is the relationship between voltage and radius, or whatever 2 variables you are plotting against each other. So you don't just have to plot voltage and radius. In fact, if you plot voltage and radius, and you find a graph that looks like this, now it's troublesome, because you know that it's exponential. But it's really not that bad. In fact, you can plug this directly into a graphing calculator or Desmos or anything that will spit out an equation for you, and it's going to say, hey, y equals, I don't know, it'll give you the m value, 2x squared or 2x cubed. You would know that it's a squared proportionality, meaning that y would be proportional to x squared, or a cubed proportionality based on the exponent that they slap right up there. Y is proportional to x cubed. Or rather, voltage would be proportional to radius cubed. Or in this case, if you got a squared value up here, voltage is proportional to radius squared. So your exponent will automatically spit out your proportionality. So if you guys know how to do that with a calculator, I say go for it. However, that's not the focus of this video, and honestly, I think if you don't learn how to do it by hand, you are missing a key component of analyzing data. And that's what this video is focusing on. We're going to look at how to figure that out by hand. So I'm going to get rid of all of this. I'm going to keep the word exponential. I'm going to get rid of everything else, though, and look at how we're going to figure that out by hand. We know it's exponential, meaning voltage is probably proportional to radius squared, or voltage is proportional to radius cubed. The way you find that out is you're going to have to plot both of them. So we're going to have to figure out voltage versus radius squared. And the way you do that is just by creating a new data table, voltage and radius squared. So whatever your initial radius was, you would square it. So let's say your radii were 1, 2, 3, 4 that you measured, and they spit out voltages of 10 volts, 20 volts, 30, 40 volts, and 80 volts. Then you would square the radii, 1, 4, 9, and 16. So we're going to plot this set of data, radius squared and voltage, or rather voltage versus radius squared. And if when you plot this you get a linear line, now you know, hey, that's the correct proportionality, right? It's going to spit out a line with some slope. Maybe the slope is 2 because that number is really easy to work with, where y equals mx. And again, b would be 0 because there is no y-intercept. So voltage would be equal to 2 times the radius squared. Or since we don't really know the slope or what it represents in this situation, voltage is proportional to radius squared. I'm hoping that things are starting to make a little bit more sense at this point. However, and if that didn't make sense, go back and rewatch that part again so it does make sense. Because now I'm going to say, okay, if that doesn't produce a linear relationship, now your thought process should be, okay, it's probably radius cubed. So we're going to do the exact same thing. We're going to make a third data table. Just like I said, we're going to try both of these graphs if the first one doesn't work out for us. So voltage versus radius squared is going to be the graph we're going to make next. Or excuse me, radius cubed. So now, just like we did before, voltage, radius cubed, and radius, you would plug in your radii, 1, 2, 3, and 4, 10, 20, 40, and 80. You would literally cube these numbers and plot them. And if that comes out to be linear, then you know that voltage and radius cubed are directly proportional. Or rather, voltage equals something times radius cubed. That's going to be the equation that physicists will use. That's going to be the equation that you'll find on your equation sheet. That's where these equations come from. Plotting this stuff out, retesting. So it's kind of a drag to have to plug in all of these values into a calculator, especially when you're working with square roots. So I'm going to show you a couple of tricks in Excel in a second, but I do want to show you inverse proportionalities because exponential and inverses both suffer from the same issue where a curve could represent two different relationships. An inverse proportionality could also represent two different things. It could be 1 over r or rather 1 over x, right? Because that could be whatever you plot along the x. Y is proportional to 1 over x, or y is proportional to 1 over x squared. In this case, we're working with voltage and radius. So when you plot your voltage versus radius, if you get this inverse graph, you're going to have to make 2 more graphs, or at least you're going to have to make one of them, hope it works, and if it doesn't, try the other one. And you do that the exact same way we did with exponential. So this graph was made with voltage and radius, where you always put your independent variable first and your dependent variable second. Your cause and then your effect, right? We changed the radius and saw how it affected the voltage. So let's say our radii were 1, 2, 3, and 4, and our voltages were 125, 160, and 10. I don't know. It's not perfect the way I did that, but you get the idea. And when we plot that data, it gave us this inverse proportionality where we don't know if voltage is inversely proportional to radius or if voltage is inversely proportional to radius squared. Well, we're literally going to have to make 2 more data tables and 2 more graphs. Voltage versus 1 over radius, so 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, or 1 0.5, 0.33, because we're physicists and not mathematicians, and we are looking for the trend. We're not looking to get pi to infinite digits, 0.25. And then your voltages would stay the same, 100, 60, and 10, and you would literally plot that into a graph. If you got a perfectly straight line, that means that voltage is in fact proportional to 1 over R. Or rather, voltage, when you plug this into an equation, equals your slope times 1 over R. So that means when you make an equation, radius would be in the denominator. That's what this is saying. That's why we're doing this. And let's say your slope is 3, it would be 3 times 1 over R. And 3 could be the product of your charges, it could be a mathematical constant, it could be a multitude of different things. That's why you would have to test different variables. So now that we know that, you should have a rough idea of how this works. However, just like exponential, if you still get a curve, whether it's this curve or this curve, we're still going to have to make our third graph that's going to be voltage versus 1 over R squared. And hopefully that will make a linear line, right? That's our goal. So the voltage would make a linear line of slope m. In that case, your equation would be voltage equals m times 1 over R squared. Y equals mx. All of this comes back to slope-intercept form, but you need a linear line for slope-intercept form to work. So you're trying different variations of your x value to produce a perfect proportionality, a perfectly straight line. So now, at this point, that's all of the conceptual information I'm going to give you. From here, I'm going to show you a couple of Excel tricks to make this a little bit easier for you, to save you a little bit of time. All right, so now that we're in your spreadsheet program or app of choice, I prefer Excel on a computer. I prefer anything on a computer, but this will be geared more towards iPads. Whoa, where am I? How do I do that? Okay, so I've already taken the liberty. Oh, I have to do it by hand. Okay. I've taken the liberty of entering the data to save us a little bit of time, but the first thing you're always going to do is plot the original relationship, voltage versus radius. And you can already look at the numbers and realize, hey, as the radius gets bigger, the voltage gets smaller. So you already know it's going to be an inverse relationship before even looking. Regardless, what have you done? Regardless, we're still going to plot the data. And to do that, highlight all of your data. And we're going to click Cell Actions. And then we're going to click Create New Chart. And you're going to scroll down to this XY scatter plot. That's the one we're always looking for, an XY scatter plot. And you can see pretty clearly this is a pretty strong inverse relationship right off the jump. Which means, like I said before, now we need to plot 1 over, now we need to see if it's 1 over the radius. So to do that, I recommend taking all of your data, highlighting it, copying it, and pasting it into a second tab, which I have up here at the top. I'm going to click right here and paste my data in. Now, we want this first column to be 1 over the radius. So I'm going to take all of this data and I'm going to hide it all the way over here. Because this second column is going to become 1 over the radius. 1 over radius. And to enter an equation, you hit this equation symbol. Let me get my pointer out. This equal sign right here. And we're going to hit the equal sign to start entering an equation. So this is going to be equal to 1 divided by the, not radius, you can't type that in, 1 divided by your cell, 1 divided by the radius. So all I did was click on that cell, and now if I hit return, it'll calculate the value for me. So now if I highlight that first cell, and you come down here, and you click on cell, we're going to autofill that same equation to make our lives so much easier. So now once we've done autofill cells, you can drag that bottom edge to fill that equation in, and it'll automatically take the inverse of all of those different radii. So I can't do that while I have my pointer up, so I'll do that myself, autofill cells, and drag it down. And now we have our inverse radius. So now we can plot voltage versus 1 over radius. We're going to again highlight our data, cell actions. Whoa, wrong button, I'm sorry. Cell actions, create new chart, and go to our XY scatter plot. Whoa, and that is not, whoops, that is not a direct proportionality, which means that our relationship based on this fake data I've made up, which is not accurate and does not reflect the data you have, is not proportional to 1 over the radius. That's what we found. Oh, there's no undo button? There it is. So now, again, if it's not 1 over radius, we have to jump to 1 over radius cubed. So again, I'm going to copy my original data to a third tab, 1 over radius squared. I think I said cubed. I'm sorry, 1 over radius squared. So again, I'm going to paste my data, and I'm going to hide the original radius values off to the side, because I'm not going to plot voltage versus 1 over voltage versus radius. I'm going to plot voltage versus 1 over radius squared. And you technically can plot all of these on the same graph, but it very quickly becomes messy. All right, so I'm going to do the same thing. I'm going to write an equation in numbers. So I'm going to come here. I'm going to go to my equation, hit the equal sign. All right, so this is going to be equal to, you always have to start your equations with equals, 1 divided by, and since I want to square the radius, or rather square this cell, I'm going to click on that cell and then square that. So I'm going to take that to the second power. And I'm not sure if you guys can see this, but this equation is being written right here. So you can double check your equation as you write it. Equals 1 divided by E2, E refers to my radius, squared. And then we can enter it by hitting return, and voila. It has automatically calculated it. And again, we're going to go down to cell, and we're going to autofill that equation down for all of my values. And once you've done that, now we're going to plot voltage versus radius squared. So cell actions, create new chart, XY scatter plot. Oh, good Lord. So this didn't really work out either. But that's because I was making up numbers, and it's not necessarily going to work when you just randomly make up numbers. But with you guys, one of these 3 graphs should hopefully, or rather one of these 2 graphs, 1 over radius and 1 over radius squared, should give you the correct relationship. And anytime you actually do collect real data and you find that it's an inverse, it should come out to be 1 over x or 1 over x squared. So one of these will spit out a linear proportionality to you. So if this one did spit out a linear relationship of slope m, then we would know voltage is proportional to 1 over r squared, because that is our x-axis, y equals mx. So voltage equals m times 1 over r squared. I hope this helps, because this is one of the most valuable skills you can have. It's extremely, extremely helpful. It's done slightly differently on a computer, but the idea is still the same. You still type equals equals 1 over e2 squared. In fact, it's exactly the same except for typing instead of clicking and drag or tapping and dragging. So I hope this video helped. If you have any questions, please let me know and I'll be happy to try to clarify them. Especially with Excel, I get kind of passionate about that. And by the way, Excel, numbers, and Google Sheets on a computer, they're all exactly the same, 99% the same, with a slightly different skin. It might have been written by different people, but they use the same equations, they use the same style of doing it. It's the same thing. I'm partial to Excel because I'm old, but you find the one that makes you happy and stick with it. I hope this helped. If you have any questions, let me know. Have a great day. Thanks.